Hello everyone, welcome to the lecture of Smart Grid. Today we will understand how the electric power system has evolved over time. So let me ask you a simple question. Do you think the power system we use today is the same as it was 100 or more 40 years ago? Obviously, the answer is no. Just like the mobile phones evolved from simple keypad phones to smartphone, the electric power system has also evolved continuously over many years. Initially, electricity was used only for lighting. Today, we use electricity for industries, hospitals, EVs, railway systems, smart homes, data centers, and many other applications. As human needs increased, the power system also had to improve. So today we will understand how this transformation took place over the last 140 years. Now students, think about our daily life. Imagine you have a mobile phone that was manufactured 20 years ago. Can you install applications like WhatsApp, Google Maps or YouTube on it? No. Why? Because today's requirements are completely different from those 20 years ago. Similarly, the first electric power system was designed only to provide electricity to a small number of consumers. As the population increased, cities expanded, industries developed, and electricity demand grows rapidly. The older power system was no longer sufficient. Therefore, engineers continuously improved the electric power system. This continuous improvement is known as the evolution of the power system. Now we will discuss the objective behind this evolution. So now the question is, why was it necessary to improve the power system? So there are several reasons behind this. So objective the first objective is growing demand, to meet the growing demand. The first reason was the increasing demand of electricity. So many years ago, electricity was mainly used for lighting. So today, almost every device around us required electricity. So due to this, the energy consumption increased tremendously. The power system also had to expand. Then second objective is to improve reliability. So let me ask you a simple question. So suppose you are admitted to a hospital and the suddenly electricity supply fails. Will it create a problem? Yes, machines like ventilators and operation theaters equipment required continuous electricity. Similarly, industries, railways, and banks also required uninterrupted power supply. So, therefore, modern power systems are designed to provide the reliable electricity with minimal interruptions. Now, the third objective is to reduce transmission losses. So, electricity is generated far away from cities. So during transmission, some electrical energy is lost in the transmission lines. So this is generally called as transmission loss. So engineers continuously develop better transmission system, higher transmission voltages and improved conductors to reduce these losses. As a result, more electricity reaches consumers efficiently. The fourth objective is to integrate modern technologies. Earlier, the entire power system was operated manually. If a fault occurs, an engineer had to physically visit the location to identify the problem. Today, With the help of computers, communication network, sensors, smart meters, GPS, then Internet of Things, artificial intelligence, and cloud computing are used in power system. These technologies make the system faster, more accurate, and more efficient. So we have discussed the objective behind this evolution of power system. In the next slide, we will discuss the evolution behind this power system. So we divided the evolution of the electric power system into five major stages. So stage 1 is the isolated DC power system. Then second stage is the centralized AC power system. Third stage is the interconnected grid power system. Fourth stage is the digital power system, and fifth stage is the smart grid. So students, now let's begin with the first stage in the evolution of the electric power system, known as the isolated DC power system. This stage existed approximately from 1880 to 1920. Before we understand its characteristics, let me ask you a simple question. Who invented the first practical electric power system? Many of you might answer Thomas Edison, and that is correct. In the year 1882, Thomas Edison developed the world's first practical electric power system. At that time, electricity was generated using direct current, commonly known as DC. Do you know what DC means? In direct current, the electric current flows only in one direction. Unlike AC, the direction of current goes does not change with the time. You have already studied this concept in basic electrical engineering. Today, batteries, mobile phone, laptops, and electric vehicles also use DC internally. So, DC is not a new concept. It is still used today, but mainly for different applications. Let us understand this system using a simple example. Suppose there is a small village with only 100 houses. A small power station is constructed in the center of the village. Electricity generated from this station is supplied only to those nearby houses. People living outside the village do not receive electricity because transmission over long distance is not possible. So this is exactly how the first DC power system worked. Generation and consumption happened almost in the same locality. Now let me ask you another question. If the electricity was generated in one location, why couldn't it be separate to another city? What do you think? Now let's understand the reason. So this is one of the most important concepts in today's lecture. Suppose you want to transport water from Nasik to Mumbai. If the pressure is very low, what will happen? A large amount of water will be lost due to leakage and friction before reaching to Mumbai. Similarly, in electrical transmission, if the voltage is low, the current becomes very high. Higher current causes higher I square R losses in the transmission line. As a result, a significant amount of electrical energy is wasted as heat. So, now we will discuss the characteristics of this isolated DC power system. So, the first characteristics is the electricity was generated using direct current. So, the current flowed only in one direction. Then the second characteristics is the operating voltage was approximately 110 volt. So compared to modern transmission voltages like 220 kV, 400 kV or 765 kV, so this voltage is very low. Then the third characteristics is generation and consumption occurred in the same locality. So this generation and consumption in the same locality. So in other words, the generating station and the consumers were located very close to each other. Then coming to this fourth characteristic, there was no interconnected grid. So each generation station operated independently. So if one station failed, there was no backup supply available. Then coming back to the fifth characteristic, so electricity was used only for lighting purpose. So at that time, the household electrical appliances were almost non-existent. Then the sixth characteristics, so the transmission distance was less than 2 kilometers. So this is very important point to remember. This transmission voltage or transmission distance less than 2 kilometers. So these are the characteristics of this DC isolated power system. Then moving to the next point, we will discuss the feature of this DC isolated power system. So the first feature is the generating stations were very small because the number of consumers was also small. Then the second feature is the distribution was completely local. Then the third feature is there were no transformers in the DC system. No transformer in the DC system. Then the fourth one is the requirement of copper. So thick copper conductors were required. So because higher current requires conductors with a larger cross-sectional area to avoid excessive heating. And the last feature would be transmission losses were very high because of the high current flowing through this conductor. So high transmission losses, that was also one of the feature of this DC isolated system. Then moving to the next point, what was the advantages of this system? So even though this system had many limitations, it also had some advantages. So first advantages is its design was very simple design. That is the advantage of this DC isolated power system. Then operation and maintenance were easy. operation and maintenance, easy, easy operation and maintenance. Then third advantage was for consumers living close to the generating station, it provided a satisfactory electricity supply. So for small towns and local areas, this system worked reasonably well. Then moving to the next part, what was the limitations of the system? So the first limitation was the high power losses. High power losses. Then the second limitation was the very short transmission distance. Short transmission distance. Then the electricity could not be supplied to the distance location. The third limitation was the voltage could not be stepped up, making efficient long distance transmission impossible. And the entire distribution system becomes expensive because of the thick copper conductors were required throughout this network. So, although the DC system was successful initially, but it was not suitable for growing cities. So, students, imagine now a city that starts expanding. New houses are built, industries are established, hospitals, schools, and markets required electricity. Can one small DC generating station supply electricity to the entire city? The answer is no. The demand for electricity kept increasing, but the DC system could not transmit power economically over long distance. Engineers realized that a completely new approach was needed. So, this challenge led to the development of the centralized AC power system, which we will be studying in the next stage. In the previous stage, we studied the isolated DC power system. The DC system could not transmit electricity over long distances because the voltage could not be increased efficiently. As a result, transmission losses were very high and the electricity could not be supplied to the nearby consumers. Now think about what happened during the early 20th century. Cities were growing, then industries were developing, railways were expanding. The demand for electricity increased rapidly. So the biggest challenge before engineers was how can we supply electricity over hundreds of kilometers with minimum losses? The solution of this problem was the alternating current power system. So this stage is known as the centralized AC power system and it existed approximately from the year 1992. So it existed this approximately from the year 1990, 1920 to 1960. So this stage completely changed the history of the electrical engineering. It is often called as the AC revolution because it made the long distance power transmission possible. That power travels hundreds of kilometers, so that goal is achieved through this centralized AC power system. So the major contributors to these revolutions were Nikola Tesla and George Westinghouse. So they promoted the use of alternating current commonly known as AC. So today almost every power system in the world is based on the AC technology. So transformer plays a very important role in this centralized AC power system. So transformer is one of the most important device in this AC power system. So it can perform two functions. So first it can increase the voltage and it can decrease the voltage. So suppose electricity is generated at 11 kV inside a power plant. So before transmitting it, a step-up transformer increases the voltage to 220 kV, 400 kV or even 765 kV. Now the electricity travels through the transmission lines with much lower current and therefore much lower losses. Near the consumer side, a step-down transformer is used which reduces the voltage to 230 volt, making it safe for household use. So this simple idea completely changed the power industry. So we will discuss the characteristics of this centralized AC power system. So the first characteristic, so the first characteristics is the centralized large generating station. Centralized large generating station. So instead of many small generating stations, large centralized power plants were established. So these power plants supplied electricity to entire cities and regions. Then second characteristics is high voltage AC transmission. High voltage AC transmission. So electricity was transmitted using high voltage AC transmission lines. This reduces transmission losses significantly. Now the third characteristic is step up and step down transformer. So step up and step down transformers became an essential part of the power system. So without transformers, the modern power transmission would not be possible. Then the fourth characteristic is one-way power flow. One-way power flow. So power flowed only in one direction, that is from the generating station to the consumer. Generating station to consumer. So consumers only received electricity. They could not generate or send electricity back to the grid. So this is also the characteristic of this centralized AC power system. And the fifth characteristic is the radial distribution system. Radial distribution system. So a radial distribution system was used. So electricity was flowed only in the one direction. So this type of arrangement is generally called as radial distribution system. So moving forward, we will discuss the characteristic of this centralized AC power system. Sorry, features of this centralized AC power system. So the biggest feature was the long distance transmission. Long distance transmission, that electricity could not be transmitted over hundred of kilometers. Then the second feature was the better voltage regulation. Better voltage Regulation. So consumers received a more stable voltage compared to the entire DC system. Then the third feature is the large thermal power plants and hydroelectric plants were established. Large thermal and hydroelectric power plants are established. Then another important feature was the adoption of the standard frequency. Adoption of standard frequency. So in India, the standard frequency is 50 Hz. So moving to the next part, we will discuss the advantage of this centralized AC power system. So the first advantage was the reduced transmission losses because the electricity was transmitted at high voltage. Reduced transmission losses. So if the current decreases, the power loss also reduces. Then the second advantage was the economical transmission. Economical transmission. So electricity could now be supplied over long distance at a lower cost. Then the third advantage was a large service area. Large service area. So instead of supplying only one village, so one generating station could now supply electricity to several cities. So that was the biggest advantage of this AC system. And finally, the overall reliability of the electricity supply improved significantly. So reliability also increases with the help of this AC power system. So these are the advantages of this centralized power system. Now we will discuss some limitations. We will discuss some limitations. So the first limitation was the consumers only consumed electricity. They could not generate electricity themselves. So that was the first limitations of this AC power system. So today many houses have rooftop solar panels. These consumers can both consume and generate electricity, but this was not possible during the centralized AC system. Then the second limitation was the absence of real-time monitoring. Absence of real-time monitoring. So if a fault occurred, operators did not immediately know its exact location. Then the third limitation was the manual fault detection. Manual fault detection. So engineers had to physically inspect transmission lines and substations. So this increases the restoration time. So as a result, the power restoration required several hours or sometimes even days. So another limitation was the difficulty of integrating renewable energy sources. Integration of renewable energy sources.